This video is dedicated to complementary slackness in linear programming. Complementary slackness is a fundamental property that relates primal and dual problems to each other and also helps us understand how both of these concepts can be used together to characterize the optimal solutions for both primal and dual LP. We will look at the primal and dual problems in the general form, as we have done in the last several videos. So we have a primal maximization problem in the canonical form, then the dual is a minimization problem in the canonical form, and assume that X star is the optimal solution to the primal problem and Y star is the optimal solution to the dual problem. So we assume that both P, the primal problem, and D, the dual problem, are optimal, and we have the optimal solutions. Since X star is optimal for the primal problem and Y star is optimal for the dual problem, we have the strong duality satisfied, and Z star, the optimal objective value for the primal, is equal to W star, which is the optimal objective value for the dual. Okay, and of course X star is feasible for the primal problem, so all the constraints are satisfied, and Y star is feasible for the dual problem. Okay, so here we have the inequalities that we had in the derivation of the weak duality property. So let me remind you what this was about. So what we did, we first used the dual constraints to get this inequality right here. So we essentially replaced Cj with an upper bound given by this sum right here. Then we switched the terms in the sum to obtain an equivalent expression just by switching the order in which we sum the terms here. And then we used the primal inequalities to obtain these inequalities right here. And in this case we were replacing the left-hand side of the primal constraint with the right-hand side of the primal constraint to obtain the dual objective as the upper bound. Okay, so and this is our W star and this is our Z star. Now, because we have Z star equal to W star, this means that both of these inequalities here must be satisfied at equality. Now let's carefully analyze what this means, that both of these must be satisfied at equality. So first, for A, what we did to obtain this inequality, we replaced every single Cj with an upper bound, right? So and then we sum all of these terms up. So for the equality to hold here, we need to make sure that for every j, Cj xj star is actually equal to the summation of aij yi stars for I between 1 and m multiplied by xj star. Alright, because we have the summation of n terms like this here, and each single one of these terms is less than or equal to the corresponding term in this sum, right? So in order to have the equality here, I need to make sure that every single of these terms on the left is equal to the corresponding term on the right of this inequality, right? So let's see when this is possible. So for xj, there are two possibilities. So xj is non-negative always, right? Therefore, if xj is equal to 0, that's the first possibility, then of course the equality holds, right? So then both sides will be equal to 0, and we have the equality here. Great. So now, how about xj not equal to 0? So if xj is not equal to 0, then it is greater than 0, right? And I can divide both sides of this equation by xj star. Now that it is positive, I can just divide both sides by it, and as a result we'll obtain the following equality. So Cj must be equal to the summation for I between 1 and m of aij's yi stars. So, and this was xj star here, right? So we are talking about x star, which is the optimal solution in the primal, and y star is the optimal solution in the dual. So we see that if xj star is not equal to 0, then we have to have the corresponding dual constraint satisfied at equality. But this means that the excess variable for this constraint is equal to 0, right? So because the excess variable is what? So it's the difference between the right hand side and the left hand side, and it has to be equal to 0 in order for this inequality to be satisfied at equality. All right, so let's denote this by ej star to indicate that this is the excess variable at the optimum when we plug in the values of yi stars in all the constraints. So this is the excess variable for the jth dual constraint at the optimum. All right. So essentially, this is equivalent to saying that ej star is equal to 0. As a result, we can conclude that one of the two variables here at the optimum, either xj star is equal to 0 or ej star is equal to 0. So the product of xj star, ej star will always be equal to 0 at the optimum. All right, so for this inequality to hold at equality, this must hold for every j between 1 and n. All right, so this is the only way we can have the equality here, and at the optimum we must have the equality. Now, if we do similar analysis for the case B, here we also must have the equality, right? And this case is going to be symmetric to the case A, because we know that the dual of the dual is primal, right? So the analysis will be pretty much the same. So let me just write down the conclusion that in order for this inequality to hold at equality, we must have the product of yi star and si star equal to 0 for I between 1 and m, where si star is the slack variable of the ith primal constraint taken at the optimum. So this is the optimal value for the slack variable for the ith constraint here. So now it's important to observe here, and this is something that we already noticed before, that there is one-to-one correspondence between the ith dual variable and the ith slack variable, because both of them correspond essentially to the same primal constraint. Similarly, the jth excess variable for the dual constraint corresponds to the jth primal variable xj star. And we can see now clearly that this complementary slackness condition essentially means that one of these two must be equal to 0 at the optimum. So for this case, it's either yi star or si star, and for this case, it's either ej star or xj star. So the product must be equal to 0, all right, in both cases. So we have this and this, and in order for us to have optimality, we have to have both of these satisfied. Okay, so because for optimality we must have equalities both here and here. So if we have the optimal solution, then both of these conditions must be satisfied at the same time. On the other hand, if both of these conditions are satisfied at the same time for a vector x star, which is feasible for the primal problem, and the vector y star, which is feasible for the dual problem, then we'll have equalities in both of these cases, and we'll have z star equal to w star. Therefore, we have x star optimal for the primal problem and y star optimal for the dual, and this becomes an if and only if condition, right? So a feasible x star and the feasible y star will be optimal for their respective problems if and only if these complementary slackness conditions are satisfied. Okay, so we obtained the optimality condition for our linear program. It's an if and only if condition. So here is the summary again. So we started by observing that when I have an optimal solution for a primal given by x star and an optimal solution for the dual given by y star, then the corresponding optimal objectives match according to the duality theorem. And then when we analyzed the inequalities that we had in the derivation of the weak duality property, we observed that since z star must be equal to w star, the only way this is possible is when either xj star is equal to 0 or the corresponding dual constraint is binding at y star. And similarly, for this to hold at equality, we have to have either yi star equal to 0 or the corresponding primal constraint satisfied at equality here. All right. So then, we can state these conditions in different ways. So let's say here the complementary slackness theorem says that if I have x star, which is a feasible solution to the primal LP, and y star, which is a feasible solution of the dual LP, then x star is an optimal solution of a primal and y star is an optimal solution of the dual at the same time, if and only if we have both of these complementary slackness conditions satisfied, right? So this is exactly what we just observed. And we can also state a different theorem which allows us to verify whether a given feasible solution x star is optimal for our problem P, all right? And this will be the case if and only if there exist numbers y1 star through ym star, so these represent the dual optimal solution essentially, such that whenever xj star is greater than 0, then the corresponding dual constraint is going to be binding, right? So you'll have the equality here. This is equivalent to saying that if xj star is greater than 0, then the excess variable is equal to 0, right? This is the only way to ensure that this product that we have in the complementary slackness is equal to 0, right? So on the other hand, if I have a constraint that is not binding at the optimum for the primal constraint, this means that the slack variable is greater than 0, right? Then if the slack variable is greater than 0, then the corresponding dual variable must be equal to 0 in order for us to satisfy the complementary slackness condition. Okay, so and of course we need to ensure that y1 star through ym star satisfy the dual feasibility. So meaning that we need to check also all the dual constraints for feasibility. All right, so let's illustrate how we use this theorem to verify if a given solution x star is indeed optimal for our problem. So here we have a linear program, and we need to check whether this vector x star is an optimal solution of this LP. There are two things that we need to look at. So whenever the primal variable is positive at the optimum, this means that the corresponding dual constraint is going to be binding. Okay, so we have this variable is positive, so x1, x2, 3, 4, x5 is positive, right? So this means that for the dual problem, the first, the second, and the fifth constraint will be binding. So let me mark this constraint that will be binding here. So this column will give us a binding dual constraint. Then this column will give us a binding dual constraint. And the fifth one will give us a binding dual constraint. Okay, so and then for the slack variable, so we need to compute Si stars, the slack variables for each constraint at the optimum. If we plug in xj stars in each constraints, then we can verify, we already have the work done for us here, that The first constraint will be binding at x star, so let's check it. So when I plug in 2, 4, and 7, then we'll have 4 here, minus 24 is negative 20, and then plus 3 times 7, 21, negative 20 plus 21 is 1, so which is exactly equal to the right hand side. So we have the equality here at the optimum, so the corresponding slack variable is 0. Alright, so then we can do the same and verify for all the constraints that the second constraint is going to be non-binding, the last constraint is going to be non-binding, but the rest of the constraints are binding at this x star. Okay, and whenever the constraints are non-binding, because we know that Si star Yi star is equal to 0 from complementary slackness, this means that whenever Si star is greater than 0, Yi star is gonna be equal to 0. So therefore, if I look at the dual variables Y1 star, Y2 star, Y3 star, Y4 star, and Y5 star, whenever the slack variable is positive, which means that the inequality is satisfied with the strictly less sign, this means that the corresponding Yi star is 0. And we'll have this for two of these Yi stars, Y2 star and Y5 star. So therefore, when we formulate the binding dual constraints, we can cross out these two rows because we know that Yi star is equal to 0 here, so these Yi stars will not contribute anything to our binding constraints. So what remains for our binding constraints is going to be 2 Y1 star, then plus 8 Y3 star, plus 4 Y4 star, and this must be equal to 18. So then we will have the second binding constraint corresponding to the column of x2. In this case, we'll have minus 6 Y1 star, then minus 3 Y3 star, and then plus 0 here and plus 0 here, right? So this is it. So this will give us negative 7. And the third constraint that is binding for the dual will be the constraint corresponding to the fifth column. Okay, so in this case we have 3 Y1 star, then we don't have Y3 star present here because the coefficient is 0, and then minus Y4 star. And this is equal to 0. Alright. So now how do we solve this system here to obtain Y1 star, Y3 star, and Y4 star? And remember, Y2 star and Y5 star must be equal to 0 by complementary slackness already. So what we are going to do, we are going to solve this system with 3 equations and 3 unknowns. For that we can use the second equation here to eliminate Y3 star in the first equation, and we can use the third equation to eliminate Y4 star in the first equation. So for that, what we need to do, we need to multiply this equation by 4 and add it to the top row, and we need to multiply the second equation by 8/3 and add it to the top row. So when we do that, so let's see what will be the coefficient for Y1 star. The coefficient for Y1 star will be 2 from here, then minus 6 times 8/3, 16, and then plus 3 times 4, which is 12. So the coefficient for Y1 star is gonna be negative 2. This will become 0. because we picked the multipliers here to eliminate y3 star and y4 star from the first equation. All right. So then we just need to compute the right hand side. The right hand side is gonna be 18 minus 56 third. 3 times 18 is 54, minus 56 third gives you negative 2 thirds. So we have minus 2 y1 star is equal to negative 2 thirds. So from here, y1 star is 1 third. All right. So now we can use y1 star equal to 1 third to compute y3 star from the second equation. So y3 star is going to be 7 minus 6 y1 star over 3. And then 6 y1 star is going to be 2. So 7 minus 2 over 3, 5 thirds. Okay, so and finally, to compute y4 star, we have from the third equation, y4 star is 3 times y1 star, which is 1. All right, so this is the solution that we obtained. y1 star is 1 third, y2 star is 0 from here. Then y3 star is 5 thirds, y4 star is 1, and y5 star is 0 from here. Now what we need to do next is we need to check that this solution y star is feasible for the dual. So far we only checked that it is feasible with respect to these 3 constraints here. In fact, these 3 constraints are going to be binding at this y star, but we also need to check that when we plug in y star in the 3 remaining constraints, then all the 3 remaining constraints will still be satisfied. So please verify that when you plug in y star into the 3rd, 4th, and 6th constraint of the dual, then all 3 constraints are satisfied. And then you also need to verify that when you plug in y star in the objective of the dual, the objective will match with that of the primal. Okay, so let's check that this is indeed the case for the objective, and then we will leave the feasibility checking for these 3 constraints as a homework. Okay, so when we plug in x star in the objective for the primal, we'll obtain 36 minus 28 is 8, and then plus 0 is 0. So the optimal objective, or what we claim is optimal z star, is 8. Okay. If we plug in this y star in the objective of the dual, then we'll have w star is given by 1 third plus 4 times 5 thirds, so 20 thirds, plus 1. So we have 21 thirds from here is 7, plus 1 is 8, so the objectives match. So the remaining thing to check is that when we plug in all the y stars in the 3rd, 4th, and 6th constraint, then each of these constraints will be satisfied. So please verify this. And this slide provides the summary of what we just did. So please again check the feasibility of the 3rd, 4th, and 6th dual constraint at y star to finalize this.
No such thing, bad student, only bad teacher. Teacher say, student do.